The second part of this lecture will be brief, but is important. We need to talk about the replacement policy in a cache, especially in this lecture that we are talking about higher associativity. In a direct mapped cache, there is no choice for replacement policy because every block maps to a single location or a single block in the cache, and whenever you need to replace something, you have no choice. You have to replace the block that you need to make space for the new block. With set associativity, you will prefer to replace a non-valid entry if there is one. So you're going to look through the entire set. We'll look in all the ways in the set. If any of the ways contains a bit valid that is equal to 0, means that that way doesn't contain valid data, you're going to place the new block into that way. Otherwise, you're going to have to choose one of the ways in the set to replace. We know that the best choice is the least recently used, but for higher associativity, we're going to have an approximation for the least recently used that we're going to use. So the least recently used will choose the one that was used the longest time ago, or has not been used for the longest time. It's very simple for a two-way set associative cache. All you need is a single least recently used bit. It's manageable for a four-way set associative cache. It's too hard beyond that, and then we're going to use approximations. Surprisingly, a random selection of which way you're gonna replace has the same performance as a least recently used for high associativity, and we saw that there is an improvement over the random one. That's the one that protects the most recently used way and replace from the other half of the set using a single bit that is easy to implement, just like the least recently used one. The next thing that we need to consider is larger block size. And for larger block size, first let's look at an example. So let's say that I have a cache that has 64 blocks and 16 bytes per block. And I want to know to which block number does the address 1200 in decimal maps in a directly mapped cache. So to do that, I'm going to draw the cache in here for you. And in this drawing, each one of those blocks should be the same size. And what I have in the end is that the block address for this cache is the floor of the division by the size of the block. So the block address is the block 75. But this cache only has 64 blocks. So how do I find the block address? Well, I go around, so I go to the block 63, and then the block 64 is at the same place as the block 0. So it's a modulo operation. So the block size will be given by the block number that was 7. So the block number that is which block I access will be the block address that was 75 modulo the number of blocks, so it will be the block 11. So that's how I find which block in the cache I accessing. But as you see, there is a better way to do that, is by simply discounting the offset bits and then looking at the bits that come after that are the bits that you use for the index. So that's how I will number my blocks up to block 63. So the final consideration in this lecture is block size considerations. So if I have larger blocks, I'm going to reduce the miss rate. You saw in that example that I was executing the loop that the instructions that came after the first instruction were all hits, because when I had a miss in the first word of the block, I brought the entire block to the cache, and the subsequent accesses were hit. So one thing that we say is when we have a larger block is that we have free prefetching, in the sense that when I do one access, I don't bring only the thing that I'm missing, I also bring some other words that are nearby. So because of spatial locality, larger blocks will reduce my miss rate. However, and that's because of spatial locality. But if I have a fixed size cache, if I make larger blocks, I'm going to have fewer blocks in the cache because the amount of space that I have in the cache is fixed. So I divide that space in fewer blocks. So I have more competition for the blocks that I have, which will increase the miss rate. So there is a sweet spot, there's a sweet point for the block size, just like there is a sweet spot for the associativity. So if I have blocks that are too large, I end up with something that we call pollution. Pollution in the cache means that I brought information, I brought data from the lower level that I never gonna use because there is a limit to spatial locality, right? So if I bring a block that's too large, I may go somewhere else before I get to the end of the block, and I end up not using several of the words in the block. The other problem is that I have a larger miss penalty because remember, the miss penalty is the amount of time that it takes to bring a block from the lower level of the cache when I have a miss. The larger the block, the more time it takes to bring the block into the cache. So that could override the benefit of having a reduced miss rate. But there is something that I can do too in some processor designs. I can do this thing that's called early restart and critical word first to help in this case. So if I have a large block, instead of bringing the block from the beginning of the block one word at a time, I could identify which is the word that I actually need to provide to the processor right away. And I could bring that word first and provide that word to the processor to try to keep the processor busy while I bring the other words in the block. So this is called the critical word first technique, and that can help when I have a large block. So I think the bottom line of this last few lectures is that there are several decisions that have to be made in the design of a cache. There is a sweet spot for associativity, there is a sweet spot for the size of the block. And one question that often occurs at this point is why there is a limit to the size of the cache. Why don't I make my caches larger? One of the main things that limits the size of the cache that I can implement in a processor is the time that it takes to access the cache. And the time to access the cache is the time, the distance to access the farthest away location in the cache. For example, for the L1 cache, I must complete an access into the L1 cache in one clock cycle because I need to provide an instruction to the processor in every clock cycle. So the size of the cache will be limited by the physical distance to the location of the block in the cache that's farthest away to access. If that gives me a one clock cycle access, if I were to make my cache bigger, my access to the cache will take more than one cycle. And remember, I need to access one instruction at every cycle. And that is what limits the design of my cache.